Jai Hind friends, myself Dr. Pankaj Goel, working as an assistant professor in EC department at Ajay Kumar Garg Engineering College. Today we will discuss another very important topic, that is polysilicon and dielectric film deposition. Deposition process is complement of etching process. As we know that in case of etching, a particular material from the top of the surface can be removed, whereas in deposition we can deposit a layer of material on the surface of the wafer. Now, film deposition is a very widely used process in the fabrication of the Vlsi circuits. These films are used for various purposes, such as the films provide electrical insulation. Dielectric films provide electrical insulation, whereas the polysilicon film provide conducting regions within the device, and as well as the dielectric layers also used to provide the protection from the environment. Some of the characteristics of this deposited films is that the thickness should be uniform, and the method that is used for film deposition should be safe and inexpensive. Now, let us see where these materials that we used for deposition have their applications are. Polysilicon is a very widely used deposition material that is used for gate electrode material in case of MOSFET transistors. Similarly, it is also used for conducting material for multi-level metallization and also used as a contact material for devices. So, these are some of the uses of polysilicon film deposition. Now, let us see how the polysilicon film is deposited. Polysilicon is deposited by pyrolyzing the silane at temperature of about 575 to 650 degrees centigrade in a low pressure reactor. The chemical reaction that is involved in the deposition of polysilicon film is SiH4 at a temperature of about 575 to 650 degrees centigrade gives us silicon plus hydrogen. So, hydrogen is a byproduct that can be removed and the silicon layer is deposited. The pyrolysis process that we are talking about, pyrolysis process is a decomposition of silane. Silane is SiH4. Pyrolysis process is a decomposition of silane through heating at a high temperature. So, that is the chemical reaction involved in the deposition of polysilicon film. There are certain parameters that affect the deposition of polysilicon, such as the temperature, the pressure, silane concentration and the dopant concentration. These are some of the important process variables in the deposition of polysilicon. Now, let us discuss what is the effect of change in temperature on the deposition rate. The effect of temperature on the deposition rate of polysilicon is expressed by Arrhenius equation, and the equation is given by R equal to A into exponential of minus Q into EA upon KT, where R is the deposition rate, EA is the activation energy in electron volt, T is the absolute temperature in Kelvin, Q is the electronic charge and K is the Boltzmann constant. So, this Arrhenius equation express the relationship between change in temperature and the deposition rate. Now, this is the Arrhenius plot for polysilicon film deposition, and this plot has been represented here for different silane partial pressure. Okay. Now, first of all, let us see in this graph, we can see that the temperature is increasing from right hand side to left hand side. Here the temperature is this 600 degree centigrade, and on the left hand side here the temperature is 700 degree centigrade. So, the temperature is increasing from right hand side to left hand side, and on the y axis we have a deposition rate, and the unit of this is nanometer per minute. Now, we can see as the temperature is increasing from right hand side to left hand side, from 600 to 700 degree centigrade, the deposition rate is increasing. As the temperature is increasing, deposition rate is increasing. That is one of the observation from this graph. The second observation is, we see that this graph has been plotted for different values of partial pressure. Here we see that the partial pressure is 1.3 Pascal, and here the partial pressure is 22.7 Pascal. So, as the partial pressure of the silane gas is increased, the deposition rate is increasing. So, from this graph we have observed two findings. Number one, with increase in temperature the deposition rate increases, and secondly, with increase in the partial pressure of the silane gas, the deposition rate is increasing. Now, what a partial pressure is? Partial pressure, if in a container there are a number of gases and each have their own pressure, then the pressure of one gas is known as its partial pressure, and the sum of all the gases together, the pressure sum of all the gases together is known as the total pressure. Now, this graph express the relationship between the silane partial pressure and the deposition rate in a different way. Here on the x axis we have the partial pressure is increasing. Here the value is 10, 20 and here 30, and as the pressure is increasing, we are seeing that the deposition rate is increasing. We can see from this curve, and slowly at a very high pressure the deposition rate is becoming saturated. So, it is becoming saturated for a given pressure. Okay. Secondly, we are also seeing that as the temperature is increasing, the deposition rate is increasing. So, this is another way of representation where the change in temperature and pressure is expressed as a deposition rate process. Now, another figure here we are seeing that how the pressure of various gases change the deposition rate. Here we can see the increase in partial pressure or total pressure change the deposition rate, but the change of partial pressure, say of nitrogen gas or the pump speed, increase the or change the deposition rate slowly, whereas if the total pressure of the gas is increased, then the change in deposition rate is more pronounced. Now, here in this figure we are expressing the relationship between dopant concentration and deposition rate. How the dopant concentration affect the deposition rate? Here we can see we have taken example of 3 type of dopants. This is boron, here it is phosphorus, and this is arsenic. Here we can see as the concentration of boron is increased in the silane, the deposition rate is increasing. If the concentration of boron is increased, the deposition rate increases. Whereas if the concentration of phosphorus or arsenic is increased, the deposition rate decreases. So we can see this in the figure here. As the phosphorus concentration is increasing, the deposition rate is decreasing. Similarly, as the arsenic concentration is increasing, the deposition rate is decreasing. Okay. Now, in this graph, in this figure, it has been shown that how the resistivity is changed. As the temperature is changed, say from 500 to 700 degrees centigrade, as the temperature is changed, how the conductivity or its inversely proportional, its resistivity is changed. So we can see as the temperature is increased, resistivity is decreased. Here we can see the resistivity is decreasing. This is on the y-axis. This is on the y-axis, resistivity. It is decreasing. Okay. Now, after discussing the polysilicon film deposition, next is discussion of dielectric film deposition. Now, in dielectric film deposition, we have 2 different kind of materials that we mainly use. One is silicon dioxide and another one is silicon nitride. Now, let us discuss about these 2. Okay. Dielectric materials are used for insulation between the conducting layers. Also, they are used for passivation to protect the device from environment, impurities, moisture and scratches. To protect device from impurities, moisture and scratches. Now, if in a silicon dioxide material, it is our dielectric material, right? So, if in a silicon dioxide material, the phosphorus is added, it helps us in the stoppage of diffusion of sodium impurities. Like if in our environment where the fabrication is taking place, there are sodium impurities and there is a chance that these sodium impurities can get mixed up, can get diffused into the wafer. So, to stop that, we can add phosphorus material in our silicon dioxide layer. Then the silicon dioxide layer is more effective in stopping the diffusion of sodium impurities. Similarly, if we use silicon nitride material as a dielectric layer, then the silicon nitride act as a barrier to the sodium diffusion. Also, it stops the moisture and has a low oxidation rate. These are some of the very important applications of silicon nitride. Now, we will discuss some of the techniques that are used for formation of dielectric layer on the wafer. The first technique involves the use of plasma process. Here, if our dielectric layer is formed in the presence of a plasma, here the argon plasma is used, then the deposition can happen by using silane gas and the nitrous oxide. Then silane gas and nitrous oxide in the presence of argon plasma at about 200 degrees centigrade gives us silicon dioxide, that is the dielectric material, then water and the nitrogen. These are the byproducts which can be removed, and silicon dioxide can be deposited on the surface of the wafer. So, this is the basic reaction between silane and nitrous oxide in the presence of argon plasma at about 200 degrees centigrade. Now, if we have to deposit a silicon dioxide layer on the surface of the wafer in the absence of plasma, then it can be done by reacting the silane gas with oxygen at about 450 degrees centigrade, which gives us silicon dioxide layer and the hydrogen. Hydrogen is a byproduct that can be removed, and silicon dioxide layer can be deposited on the surface of the wafer. So, that second process involves use of oxygen instead of nitrous oxide, which is being used in case of plasma. Okay. Now, let us discuss the third method of silicon dioxide deposition. Here, in this case, instead of silane gas, we are using dichlorosilane for the deposition of SiO2. Now, this dichlorosilane in the presence of nitrous oxide at about 900 degrees centigrade gives us silicon dioxide layer, nitrogen and HCl. These are the byproducts which can be removed. Okay, so this is the third technique in which dichlorosilane is used. Now, in the fourth technique, there is another material that we are using is tetraethoxysilane. Tetraethoxysilane is the material that is used in this fourth technique, and in this case, this tetraethoxysilane at about 700 degrees centigrade temperature is decomposed, provide us silicon dioxide and some byproducts which can be removed in the due process. So, these are the four different techniques, methods for the deposition of silicon dioxide on the silicon substrate. Now, after discussing the deposition of polysilicon and silicon dioxide material by different techniques, next topic of discussion is the deposition methods. There are three methods that are predominantly used for the deposition of polysilicon and dielectric material. These are known as atmospheric pressure CVD, where CVD is chemical vapor deposition technique. Second one is low pressure CVD, and the third one is plasma enhanced CVD. So, these are the three methods which are mainly used for the deposition of polysilicon and dielectric film deposition. Okay. Now let us discuss the schematic diagram of these three methods one by one. First of all, let us discuss the schematic diagram of low pressure CVD. Here in this case, the main components that are shown here is the pressure sensor, load door. Pressure sensor is used to monitor the pressure inside the reactor. Load door is basically used to load and unload the wafers. These are the samples or wafers. Okay. So, and this is the wafer holder. We can say this is the wafer holder. So, this load door is used to load or unload the samples or wafers from the reactor. Now, this is the quartz tube and this is the exhaust pump. This is the gas inlet. Silane gas and other gases like nitrous oxide, these are provided through this inlet. And this technique uses 3-zone furnace. That is, the 3-zone furnace is used to heat up the reactor, and this 3-zone furnace has the advantage that it provides very controlled temperature throughout the reactor. Okay. Now, some of the features of this low pressure CVD. Low pressure CVD is also known as hot wall reduced pressure reactor, and it is used for, it can be used for the deposition of polysilicon, silicon dioxide as well as silicon nitride. So, LPCVD method can be used for the deposition of polysilicon, silicon dioxide as well as silicon nitride. The reactor consists of quartz tube heated by a 3-zone furnace, and the pressure in the reaction chamber is typically 30 to 250 Pascal, temperature in the range of 300 to 900 degrees centigrade, and the gas flow is between 100 to 1000 standard cubic centimeter per minute. Wafers stand vertically perpendicular to the gas flow, and these reactors can hold wafers of size around 150 millimeter diameter. 150 mm diameter wafers can be used. In each run, in each shift, the process can have about 50 to 200 wafers, and the thickness uniformity is within the range of plus minus 5% tolerance. So, the advantages of this method is excellent uniformity, large load size and ability to accommodate large diameter wafers. So, these are some of the advantages of low pressure CVD technique. Some of the drawbacks are low deposition rates and frequent use of toxic, corrosive and flammable gases. So, these are some of the drawbacks. This is an example of atmospheric pressure CVD reactor. Here we can see on the top there is the gas inlet, then there is a heater inside the reactor, and there is a conveyor belt which is used to move the wafers for the proper uniform deposition of silicon dioxide or polysilicon material, and in the bottom there is exhaust. So, this is about APCVD reactor. Now, quickly let us discuss the plasma enhanced CVD reactor. as we know that plasma is any gas in which a significant percentage of the molecules are ionized. Plasma enhanced CVD is a chemical vapor deposition process used to deposit thin films from a gas state to solid state, because we know that the ionized molecules are in the gas phase. So, they are deposited in a solid state on a silicon wafer. So, this is a schematic diagram for a plasma enhanced CVD. Here we can see these are the gas inlets and this is the exhaust out. These are the wafers and the wafer holder. This is the plasma. This is the RF input, radio frequency input, which is used to provide the ionization of the gases. These are the electrodes, aluminum electrodes, which provide the discharge for the plasma generation. Okay. Now, some of the advantages and drawbacks of this. The advantage is that it works at a low deposition temperature. It is a very important benefit of it, that this process can work at lower temperature, because at higher temperature we know that there is a drawback of auto diffusion, that is auto doping, where the already deposited dopants inside the wafer can come out and they can be deposited on these layers of polysilicon or dielectric material. So, that auto diffusion of the dopants can be stopped if the process is worked at lower temperature. But some of the drawbacks of the plasma enhanced CVD is limited capacity, and wafers are to be loaded and unloaded individually, and wafers may be contaminated by loosely adhering deposits falling on them. So, these are some of the drawbacks of plasma enhanced CVD. The book that has been used for the preparation of this presentation is Vlsi Technology, written by SMZ from McGraw-Hill Education. For more detailed study, this book may be referred. Thank you very much.